So we're going to see another basic principle of combinatorics. Your book calls this the subtraction rule, and it goes as follows. Okay, it's similar to the sum rule. So if we have, or well, let's say if choosing something means making one choice or another, right? So this is the setup is the same as for the sum rule, but in the sum rule we said that the choices can't overlap. So what if they do overlap? Right? So in this case, but the choices overlap. Right, then the total number of choices is number of choices for the first choice, number for the second choice, and then I subtract the number of choices in common. Right, because if there's overlap, when I add these, any choice that overlaps, I've now counted twice. Right, I counted it once in here and I counted it once in here. So we just have to subtract those, and then once we subtract them, we will only have counted them once. And we've seen this before, right? We've seen this in the form of this formula for the size of a set union. Right, we said, well, this is the same as A, size of A plus the size of E minus, we have to subtract off the things in common. So this is called Principle of Inclusion-Exclusion. Right, or PIE for short. So, right, we did one example in the activity in class where we had these two restaurants and you could choose something to order from one restaurant or the other, but there were some things they had in common, and so you had to add them and then subtract off the number they had in common. Here's another example. How many strings of 8 bits, right? So I have 8, a bit is either 0 or 1, so I have 8 of them in a sequence, right? So 0, 0, 0, a bunch of zeros, or I could have 0, 1, 0, 1, 1, 0, 1, right? So any of those possible strings of 8 bits. So how many of them either start with a 1 or end with 0, 0. Okay. So I'm going to count the number of strings that start with a 1 or end with 0, 0. So first of all, right, how many start with 1? Well, if it starts with 1, then I don't get to choose that. It's just fixed. But there's 7 more bits after that, and I can choose those to be whatever I want, right? Any choices I make, I'm still going to have a string of 8 bits that starts with a 1. And so I can choose each bit independently, and so I have 2 choices for each bit. So I have 2 choices for each of the remaining 7 bits. So that gives me 2 to the 7th strings, binary strings of length 8 that start with a 1. And, right, how many end with 0, 0? Of course, now I don't get to choose the 0, 0, but I can choose the first 6 bits, so that's going to be 2 to the 6th. Okay, so I want strings of 8 bits that either start with a 1 or end with a 0, 0, so I can use the sum rule, except, right, these overlap. There are some strings that both start with a 1 and end with 0, 0, so I can't just add these. Okay, so what I need to do is figure out how many are there in the overlap. So how many start with 1 and end with 0, 0? Well, again, this is going to be very similar because now I've got 3 bits that are fixed, and I still have 5 in the middle that I get to choose. So that's going to be 2 to the 5th. Hence, the total is 2 to the 7th plus 2 to the 6th minus 2 to the 5th. All right, I add up the possibilities, then I subtract off the overlap. And again, you can use a calculator if you wanted to know what this is. I think it's 160. But again, figuring out that it's 160 by listing all the possibilities is not going to work. But by breaking it down using the sum rule, and also we use the product rule, right? We broke it down in terms of these principles, and we're able to calculate it. I want to show you one more thing, which is, so I'm going to leave this actually. So here we have, right, this is the subtraction rule if I have 2 sets. What if I have 3 sets? So remember we had the product rule, we generalized it to work with any number of things. And the sum rule, I didn't say this, but clearly it can be generalized as well, in the sense that if I have n different choices and I get to make any one of them, I get to basically choose which choice I'm going to make and then make that choice. And if none of them overlap, then we just add them all, and that's very easy. But what if they do overlap? If I have more than 2? So I just want to show you how to derive the result for if I have 3 sets. And we could talk later about how to generalize it further. But if I have, so the question is, if I have 3 sets and I want to sort of union them all together and figure out how many things I have, but in general they could overlap, right? What is this going to be? Well, first of all, let's notice that union is associative, so I can add some parentheses like this, and now this looks like one set union with another set, so I can actually apply this rule here. So this is going to be size of my first set, A union B, plus the size of the second set, C, minus the size of their intersection. So A union B intersect C. Okay, well now here I have the size of a union of 2 sets, so I can apply that rule again. So here I'll get size of A plus the size of B minus the size of A intersect B, and then I still have this plus size of C. And then here, let's see, so intersection distributes over union, so I can distribute this over here. So I'm going to get minus A intersect C union B intersect C. Let's see, so now this is all kind of settled, but we need to do this. So this is now, again, we have the size of a union, so we can apply this rule yet again. So I still have size of A plus size of B. I'm going to move the plus size of C over here because it just kind of goes with these other things, and then I'm going to do minus A intersect B minus, and now I'm going to apply this rule, so I get the size of A intersect C plus the size of B intersect C minus their intersection. A intersect C intersect. So right, the size of this plus the size of this minus the size of their intersection. And notice here, so we can simplify this a lot because set intersection is associative so we can kind of get rid of the parentheses. It's commutative, so we can switch the order of things around. And then finally, it's idempotent. So in particular, I have a C here and a C here. I'm just doing a bunch of intersections. So C intersect with itself is just C. So I can basically just get rid of one of the C's and just write A intersect B intersect C. And then I'll just like distribute out this minus. So finally, what I get is A plus B plus C minus A intersect B minus A intersect C minus B intersect C. And then finally, I have a minus here, so minus a minus is plus. And I'll write it down here, plus the size of A intersect B intersect C. Okay, so there you go. So this is the analogous version of the principle of inclusion-exclusion for 3 sets. Here we had it just for 2 sets. Right, so this says if you want to count the number of things in this union, first just add up all the sets, but then you might have counted some things twice that were in the overlap. Right, so let's subtract off anything where A and B overlap. We'll subtract anything where A and C overlap. We'll subtract anything where B and C overlap. But then it turns out there's some things we might have subtracted too much. In particular, if there's anything that's in all 3 of the sets, we added those things 3 times here, but then we subtracted. So like, let's say if I have one thing that's in all 3 sets, right? I added it 3 times here because it's in all 3 sets. And then I subtracted it 3 times here because it's in each of these. So now I've counted it 0 times, so I need to add it back. And so that's why we add this back at the end. And you can do the same thing and derive this for 4 things and more. And you'll see that it's going to follow this same kind of pattern. Kind of a fun exercise to try doing this same exercise but for 4 sets and see if you can derive what this is.